예, 저번 시간에 이제 우리는 그 컴퓨터 시스템이라는 것이 어떤 것인지, 그리고 이제 컴퓨터 아키텍처, 이 컴퓨터 구조라는 과목이 컴퓨터 시스템에 대해서 어떤 분야, 어떤 것을 이제 다루게 되는지, 뭐 그런 거를 조금 인트로덕션 형식으로 이제 다루었습니다. 그래서 이제 지금, 이번 시간에는 그 챕터 1 파트를 조금 더 이제 진행을 하고, abstraction과 그다음에 컴퓨터 퍼포먼스를 어떻게 이제 우리가 measure를 할 수가 있는지를 조금 더 다루도록 하겠습니다. 어쨌든 뭐 우리가 이제 저번 시간에 여러 가지 형태의 컴퓨터 시스템을 이제 보게 되었고요. 특히나 이제 중요한 거는 우리의 그 일상생활에 이런 컴퓨터 시스템이 진짜 pervasive하게 아주 널리 퍼져 있다는 것이죠. 그 다음에 이런 디바이스에 대해서 우리가 다루게 될 때 그 컴퓨터의 하드웨어, 그 다음에 이제 컴퓨터의 하드웨어를 돌리는 소프트웨어를 우리가 모두 잘 연구를 해야 되고, 그 디바이스가 어떻게 하면은 더 better device가 될 수 있을지, 우리가 그 분야의 그것을 연구하는 것이 이제 우리가 이제 컴퓨터 아키텍처, 컴퓨터 구조라고 우리가 이제 나누었습니다. 예. 그래서 이제 결국에는 우리가 이제 better 컴퓨터 시스템을 이제 만들어야 되는데, better 컴퓨터 시스템은 performance, the higher performance with lower cost를 가지는 그런 컴퓨터를 만들어야 된다라고 그렇게 이야기를 했었죠. 그래서 무엇을 배울 거냐? 이 과목에서 여러분들이 어떤 것을 목표로 배워야 되는 것인가에 대해서 조금 이렇게 나누었습니다. 그래서 이제 무엇을 배울 것인가 또 이제 우리가 나눴죠. 자, 그러면 이제 지금부터는 이제 abstraction에 대해서 이제 우리가 좀 나눠보도록 하겠습니다. So from now on, I will talk about the abstraction of the computer system. So do you remember the goal of this course? So I said that the goal of this course is exploring computer system architecture at an abstraction level. So in the sentence that represent the goal of this course include the word abstraction. Then what is an abstraction of the computer system? So this slide shows the analogy of abstractions. So let's think about the car driving. So if we want to drive a car, so then do you need to understand everything of a car? No. So actually a car is composed of engine, brake system, and many other components, small devices, and then systems. But the knowledge on the car engine or knowledge on the brake is not required to drive a car. Why? Because its detail of this car system or detail of a car is hidden to the car user. Who is a car user? Those who drive a car. But this detail of car system is hidden for the user. Why? Because the car user doesn't need to understand how the detailed system of a car. So the only thing we need to learn to drive a car is to rotate the handle and then press the brake pedal, and then just learn some operation of this car system, like what's it, 깜빡이? It's a direction lamp and how to operate some headlamp and then some systems. That's the only thing we need to learn to drive our car. It's a very small part of a car system. But if we only know to drive a car, then we cannot make a car system. We don't know how to make an engine. We don't know how to design a brake system in a car. But for car user, the only thing need to learn is to drive a car. The complex part is hidden to the user. And then how about the car designer? Car designer does a car designer understand how to build a car engine or a car brake system? No. This system is hidden for car designer. Car designer only design some car interior or car chairs or some, and then car exteriors, not inside of the car. The inside of the car, and then how to, and the inside the component of the car is hidden to the car designer. So this is the analogy of abstraction. For the car driver, details are hidden. Only the necessary knowledge or necessary information is revealed to the car driver. This is called the abstraction. Okay, then let's talk about the definition of abstraction. What is abstraction? Abstraction means hiding details when they aren't important. When they aren't important or not important. So how can we decide which is important and which is not important? So and then meaning of abstraction is to provide only required interface information between two adjacent layers. So in this meaning of the abstraction here, so we only require interface information. So what is the interface information? It's some port or some protocol between two layers. So only this information is revealed to the upper layer, and then for the bottom layer, but the upper layer doesn't know the detail of the bottom layer. It's also the meaning of abstraction. So let's think about the abstraction of the computer system. This figure shows some several layers of computer system. So if we see the computer system, the computer system is just the hardware, but we say that the computer system include the software and hardware part. If a software doesn't run on the computer system, then that computer system is just a 깡통, a can, a metal can. It's just some object, meaningless object. 그래서 깡통. 보통 이제 깡통이라고 부르죠. 네. So if software runs on the computer hardware, then the computer becomes the meaningful object. So let's think about the layer of the computer system. The most top layer, the most upper layer is the application software. So what is the example of application software? So web browser and office software or games. So actually user interact with this application software. So, and then this is the most level of the computer layer. It's a program just interact with the computer users. And then under this application software, there is an operating system. It's also Operating systems are also kind of software, but this software controls the computer hardware, also manage the resource of computer hardware. So this operating system communicate with application software, and then this operating system also communicate with bottom architecture, instruction or registers. It's a computer hardware. So what is the interface? This is some protocol or promise between these two layers. So application software doesn't know how operating systems work. It just understands the interface between operating system, such as the library or API provided from the operating systems. This application the software engineer which try to design the application software do not need to understand about the operating system. And how about this operating system? The operating system engineers do not need to know about the detailed hardware of the computer system. We just the operating systems engineer only need to understand the interface between this OS and architecture of the computer system. And then this interface can be is the instruction set architecture is the one of these interfaces. And then under the operating system, there is the architecture of the computer system. This is some higher level architecture of computer system. So this architecture means some organization of an entire computer system, such as CPUs, memories, storage, GPU, and some interconnection between these devices. This is the higher level architecture of the computer system. And then under this higher level architecture of the computer system, there is the process architecture or the micro architecture. This micro architecture covers some detailed abstraction of the CPU or core or some arithmetic unit or some engine of the single core. This is called the microarchitecture. And then under the microarchitecture, there is a logic. And then if you took the logic design course, then you can understand what logic is. So the example of logic is some small digital logic, such as the adders or memories, like some memory cell or SRAM cell. Adders, subtractors, and multipliers, these are the kind of arithmetic logic. So this is the logic, and then this microarchitecture is composed of logic and the connection and control unit for these logics. And then this logic is composed of digital circuits such as AND or NOT gate. So these are the basic gate of the digital circuit. So if you want to design the adder unit, then you need some this basic digital circuit like a AND or exclusive OR gate. And then if we compose this gate, and then we can make some basic logic. And then under this digital circuit, there is the analog circuit. So actually this AND gate is the analog aspect. This AND gate or it's a NOT gate is the kind of amplifier. Yeah, so actually our knowledge can start from this how to design a detailed NOT gate, but this is the kind of analog circuit knowledge. So if you are a digital circuit engineer, then you don't need to understand how some knowledge regarding the analog circuit, but you need some a little bit knowledge on the analog circuit, but not detailed knowledge, because you need to understand some interface between digital and analog. And under the analog circuit, there is the device, such as the transistor or diode. So actually, it's the CMOS transistor. CMOS transistor is the kind of device. So CMOS transistor is composed of PMOS and NMOS, and then the property of this PMOS and NMOS is determined by some channel lengths and then some density of the electron, or density of the donor, or something like that. So if you want understand the property of this MOS transistor, then you need to understand the device. It's a very low level. And under this device, we need to understand the physics of the electrons and the materials. And then this so it's like electrophysics. So these are the layer of the computer system. And then actually, in order to make a better computer system, or in order to make the entire computer system, all of these knowledges is required. So if we don't have any knowledge so people don't have any knowledge on the physics or device, then we cannot build the computer. Actually, the base of this computer system starts from the knowledge on the analog circuit, device, and physics. But as a computer architect, or software engineer, or operating system engineer, we don't need to detail the bottom layer of the computer system, such as this one. Actually, as a computer architect, we don't need to know about the detail of this circuit. No, it's not always true. But if you focus on the research on this computer architect, then the knowledge on this part can be not unimportant, not critical. As an undergraduate student, but you need the knowledge on the digital logic or digital circuit, computer architecture, and operating system, and programming language, because we are all computer engineering student. But if you focus on some specific area of the computer system or specific layer, then you focus on this layer, and then the other knowledge is such as some logic or digital logic can be unimportant knowledge. So you need to know, but it can be non-critical. 그러니까 사실은 우리가 이제 컴퓨터 엔지니어링 스튜던트로서 이건 다 배워야 되죠. 우리가 이제 디지털 로직 디자인도 배웠고, 그 다음에 지금은 아키텍처를 배우고 있고요. 그 다음에 이제 좀 더 시간이 흐르면 오퍼레이팅 시스템도 배울 거고, 그 다음에 프로그래밍 랭귀지도 배울 거고, 알고리즘도 배울 거고, 이런 거 다 배우게 됐죠. 그렇지만은 보통은 이제 우리가 포커스해서 일을 하게 될 때는 이렇게 우리가 여러 가지 레이어로 이제 나누어지는 영역에서 우리가 어떤 영역을, 어떤 레이어를 좀 더 집중적으로 연구할 것인가, 일을 할 것인가, 이렇게 이제 집중을 해가지고 우리가 이제 연구를 진행하거나 스터디를 하게 되겠고, 그럴 경우에는 이런 다른 레이어의 이제 디테일한 것에 대해서는 조금 무시를 해도 좋다. 그 다음에 항상 우리 한 사람이 모든 거를 다 하는 거는 불가능하기 때문에 우리는 이제 다른 사람과 협업할 때도 그렇고, 여기에는 우리는 여기에 이제 집중을 하게 되고, 다른 레이어랑 협업을 하게 될 경우에는 인터페이스 인포메이션 이런 데 이제 집중을 하게 되는 거죠. So this is the abstraction, and this abstraction concept is very important for computer engineering area. Okay, and then in this course, we will cover the architecture of the computer system And then in detail, we'll cover the computer organization architecture, computer organization, and microarchitecture of computer processor. Okay, let's see some simplified layer of the computer system. Actually, we focus on the hardware and software. Okay, if we only see some hardware and software of the computer system, we can divide the computer system as the three layers: application software and system software and hardware. So actually, these two layers are related to the software, and then this is the hardware. It's related to the computer architecture. So application software is written in high-level languages such as Python or C or C++. Compared to the C or C++, Python is the higher level language because it's easier than C or C++. But we code is C, C++, Python as the high-level language because this programming language is very similar to our natural language, such as English. And then system software. So system software there are two kinds of system software: compiler and operating system. So compiler translates the high-level language to machine language. So actually, the computer hardware cannot understand the high-level language. It cannot understand because there are many variants of high-level language, but then computer hardware can only understand some defined instructions. So compiler translates this high-level language into the machine language, and then machine language can be mapped to some computer instructions. And then operating system. Operating system manage the computer hardware. So handle the input and output of the computer system, and then manage memory and storage, and then schedule tasks and share resources. How about the hardware? Hardware to compose of the CPUs, memory, some I/O, and then network is some hardware component. So if the software is translated into the computer instructions, and these computer instructions are executed in the computer hardware, and then we can see the result of the application software. Yeah, so this is the level of some program code. So as I explained, there are some levels of the program code. So the high-level language is very similar to our natural language, and then only the software programmers write the programs or code with the high-level language because it is easy to understand for normal people. It's normal human. So this high-level language is designed for high productivity and portability. So if we see the program written in high-level language, then we can easily understand. And then this high-level language is translated into the assembly language. This assembly language is very similar to the machine language. And then you can see there's some instruction and then registers and operand of the instruction. So this is the example of assembly language. So if you invest some time, then you may understand how this assembly language works, but normally it's very complex. It's not easy to understand, and then normal people actually cannot understand how this assembly language works. Now, how do a presentation? The most of the electric devices handles the only digital signals. So digital signals means that this signal can be represented as the 0 and 1. All values will be represented as the 0, low, or off, and 1, on, and voltage is high. So this machine language assembly code is translating to the machine language or digital code. And then if the digital code is input to the computer processor, the computer processor fetch this digital code, and digital code is executed by the computer hardware. So some also different layers. So the compiler, so from from high level to the assembly language, compiler translate the from higher level language to the assembly language, and then also assembler translate the assembly language to the binary machine language. So yeah, this is the die photo of Intel i7 processor. So if you see this die photo, then yeah, it is so beautiful. Then can you understand how this hardware works, and can you understand which part is which part is CPU, which part is SRAM, which part is cache? So we can now understand how the hardware of this die. We can understand the hardware of this CPU if only we see the port of this CPU. So yeah, it just looks beautiful, and that's it. It's just a photo. How about this? This is some abstraction of the inside of a processor. So as you can see, this is the level 3 cache. This is the mark of the cache memory. And this is the CPU core. And this is the interconnection. And this part is the GPU. And then this is a system agent. And then this part is the memory controller. So this is another example of the abstraction. If we see this photo, and then we can see everything, not everything, but we can see some structure of the Intel CPU, but we don't know which part, how the we cannot understand which part is assigned to which location of this single CPU chip. But if we see this figure, then we can figure out which part is located in its location of the single CPU chip, and then we can know also the composition of this single CPU. So if we see this photo, we can know that there are 4 cores in the CPU, and there is a level 3 shared cache, and then the interconnection is connected between among these 4 cores of CPUs. So we can know the GPUs are included in this CPU chip. How? The components are presented on this die photo, so we can see which component is included in this CPU chips. This is also kind of abstraction. So abstraction helps us deal with complexity. So as I said, only for the abstraction hide the unnecessary detail of the computer system. So it only shows some required knowledge on the abstraction level. So as a computer architect, we can understand some computer system as some block diagram, and then connection, and then control signals. Yeah, this is also kind of abstraction. Also, instruction set architecture. This instruction set architecture is the interface between hardware and software. inside of the process. Actually, every CPU family has the instruction set architecture because the hardware is designed by contraction of the instruction set architecture. Yeah, so this is the architectural view of the processor. So I said this is the architectural view. This is the photo. This is just a photo. And then we can understand by the some component of the computer CPUs. And then this is the architectural view of a single core CPU. So in this figure, you can see only boxes and arrows and some connections or something like such like that. But and then some titles on the boxes. But if we analyze this architectural view of the single core CPU, then we can understand how how a single core CPU is organized and how the component of the CPU is connected, and then how the signals and data flow from one component to another component. So we can understand how CPU works with this architectural view. If you take some computer architecture course, if you study on the research in the area of the computer architecture. So, but details are hidden in this architectural view. What is the detail? Some arithmetic logic or some digital logic is hidden in this figure because it's very complex and we don't need to understand it as a computer architect. We just only show boxes and connection, and that's it. That's how the computer architect understand the computer hardware. And then this architectural view is very important for the also digital designer. Actually, the most recently the most of the chip is very complex, and then so it's a complex that the most of the chip is called the system on chip. So that means that very complex systems are implemented as a one single chip. So we need to understand the architecture of this SoC or some data flow or block diagram and then some components of the various components of this SoC. So architectural knowledge is also important for digital system designer. Also, this architectural knowledge is also important for software engineer, such as the system software engineer or operating system designer. Also, this is very important for computer architect. Okay. So these are also components of the computer system. The computer system include the user interface, storage, and network, and then some other component. So, okay. Okay, let's talk about the technology behind the computer systems. This technology, the advance of the computer system comes along with the advance of some semiconductor technology. Okay, let's see the technology trend. So, we know that the channel length of the CMOS transistor is reduced to every process or every year. So when I was a the first graduate student, the channel length of the CMOS transistor is something like micrometer, kind of tens of micrometer. But nowadays, it is under 10 nanometer. It's very, very short compared to the micrometer ranging. So what is the benefit of this short width of the CMOS transistor. What is the benefit? The devices get faster, so that means they operate faster. Also, the operation voltage can be reduced. That means that this revised device, the small size of device, will consume lower power. Also, I said that this is small size of device, so size is also shrink. That means that in the same area, we can include more number, the more transistors. So that means the larger number of transistors. So yeah, this graph shows the capacity of DRAM. So you can see this. Okay. This x-axis means the year of introduction, and then the y-axis is the kilobit capacity, and then you can see the y-axis is the log unit. So it's a log size. So that means that, so even though this graph looks linear in the by x and y axis, but actually this graph is exponentially increases. So that means that for every year, the size of the DRAM and then the capacity of DRAM increases exponentially. It's so huge. So I said that the advance of computer system comes along with the advance of the IC technology, semiconductor technology. So actually the computer system starts with the vacuum tube. So and then in the 1965 transistors are invented, but the vacuum tube is very huge and then it consumes very large energy or large power. But transistor size is much smaller than the vacuum tube. And then the integrated circuit is invented, and then VLSI, and then ULSI. So this is the relative performance per cost. So as you can see, the performance is improved very much, exponentially. So we cannot compare the performance of ULSI and the vacuum tube. We cannot compare. It's very, it's about the 1,000 million, billion, the 250 billion times better than the first vacuum tube. So this is some manufacturing process to make the integrated circuit, but it's not important in this course. But the integrated circuit starts from this silicon cylinder, and then we slice this silicon cylinder and to make the wafer, and then the IC, the chip or CPU chip, is fabricated on the surface of this wafer. So actually, the wafer has the shape of the wafer is a circle, but the shape of chip is a rectangle or a square. And then this fabricated on the surface of the wafer, and then we tested each die, and then if the die is dead, So if there is the defect on the die, then the die is removed. So it's dressed away. So to test the die, and then we only select the undefected die, and test this package, and then ship to the customers only for the working chip. So that means that, so in this manufacturing process, I said there are many test steps. So test the surface of the wafer, and test the die, and test the package, and test the operation of the chip. So this test process is performed, and then defective chip or defective wafer is thrown away, kicked out. So yield is a very important factor. Actually, the yield is the proportion of working dies per wafer, and this yield is a very important factor for this chip industry. So this photo is some photo of the i7 wafer. As you can see, this wafers, the shape of the wafer is the circle, and then the rectangle i7 die is fabricated on the surface of the wafer. So as you can see, you can see this die cannot have a rectangle form, so just throw away. So we can only use this entire rectangle die inside of the wafer. So this is the cost per die. This is very important because we are engineering students and we are engineers. The cost is actually the most important part of the engineering. So cost per die is equal to the cost per wafer divided by dies per wafer multiplied by yield. So yield is the range from 0 to 1. 1 means that all chips are good, so we don't need to throw away any dies, but it's not possible. It's an ideal case. And then, so yield has the range of 0 to 0 between 1. The good thing for Samsung is that Samsung can manage the yield as the very high value. It's also technology, and then it's some 기술력 for some in the company's 기술력. Okay, until now I will talk about some background of the IC technology under the computer hardware, and then I will explain about the performance of computer system or computer hardware. Okay, let's start from some real example. So this graph shows the various performance of airplanes. So let's see, the first criteria is the passenger capacity. So as you can see, Boeing 777 can deliver about 350 passengers with the one airplane. And then 747 is the bigger airplane. And then the cruise range is some distance when if the airplane is fully fueled, and then speed, and then this passenger multiplied by speed. So these are different criteria to measure the performance of airplane. So can you say which airplane has the best performance? So if you focus on only passenger capacity, the Boeing 747 is the best airplane. But is that true for all cases? No. Sometimes speed is important, and then overall the speed multiplied by performance can be important. So we can apply the different criteria of performance metric for airplanes. And then the performance of the airplane, the best performance of airplane is determined by the different performance criteria. So let's think how the performance is measured for computer systems. So how can you say for the performance of a computer system? So what is important? We frequently say my computer is very slow, works very slow. So what does that mean? If the software or application is executed on my computer, then execution time is long. That means that the computer is slow. Then we don't like slow computer systems. So if computer is too slow, then we will replace our computer systems to the faster one. So what is the criteria to measure the performance of the computer system? Execution time is this one. The response time is sometimes called the execution time. Then execution time measured how long it takes to do a task. So actually we are very familiar with this performance metric because we always say my computer is slow and my computer is fast, and your computer is very good because your computer is very fast. So we always say response time or execution time to compare the performance of my computer and your computer. But we can say another performance metric is the throughput. Throughput is defined as the total work done per unit time. So actually this throughput is related to the amount of task performed during the same time or during some certain time frame. So actually the response time measures the execution time from start to the end, but throughput measures the amount of workload. So we can say that if the computer is fast, then it can do more jobs during the same time. That's true for the single core processor, but it's not always true for the multi-core or parallel processors such as GPUs. Because GPU is very actually very expensive because throughput is very high for GPU, the graphics processing unit, because the GPUs are designed for efficient parallel processing. So firstly, we will focus on the response time now, because it's very familiar to us, and then we always say, my computer is fast, and your computer is slow, and my computer is slow, your computer is fast. So we focus on the response time now. So how can we measure the response time or execution time? Just measure the time between start to the end of the program. So we say that if the execution time is long, then performance is low. And then we can say that if the execution time is short, that means that the program runs very fast, then performance is high. So performance and execution time is inversely proportional. So we can say that performance is equal to the inverse of execution time, and we can say that. So if the computer X is n times faster than computer Y, that means that the performance of computer X is n times higher than the performance of computer Y. That means that, so I said that performance is the inverse of the execution time. So if we compare the execution time of X and computers X and Y, then that means that is the execution time of computer Y divided by execution time of computer X. Then is equal to n. So actually you need to let me see, memorize this one. So important. So this is the example. Time taken to run a program here, and then it takes 10 seconds on the computer A, and then it takes 15 seconds on computer B. So let's compare the performance of computer A and B. So we can compare the execution time of computer B and computer A. So execution time of computer B is divided by execution time of computer A, then the ratio becomes 1.5. So that means that computer A is 1.5 times faster than computer B. That means 50% faster than the computer B. And then this elapsed time, so it's the total response time of the application or user software, include many aspects or many overhead. Because let us assume that we pressed some key and then no. So let us assume that we are playing game and then we are using mouse. We use the keyboard and then we press some keys for the game. So actually, the entire performance of a game software and a game application is related to the input and output devices, and then also the software runs on the operating system. So the operating system overhead is also including the final execution time. Also, the CPU does not work every time. Sometimes CPU goes to idle time because we don't give any inputs from the I/O. So this idle time is also including the total response time. This is because the software is very complex. The software is composed of many operations, and then these overheads are included in the overall execution time. So it's very complex. So we only focus on the computer hardware, and we only focus on the CPU, computer processor. So we just remove the overhead or aspect by this I/O, operating system, or idle time, and then some other interfaces, and then we can just only compare the execution time on the CPUs. So this is the time spent processing a given job. It only considers the CPU performance. 예, 강의 녹화를 하다가 그 컴퓨터가 오류가 나가지고 다시 이제 녹화를 하게 되었습니다. 다행히 그 강의 녹화를 하던 파일이 임시 파일에서 이제 찾을 수가 있어가지고 그 뒷부분을 이제 녹화를 하면 되는 상황인데, 뭐 그래서 이제 뭐 동영상 자르기, 붙이기 이런 식으로 또 해야겠네요. 어쨌든 뭐 여기 이 슬라이드부터 이제 시작을 하겠습니다. So I explained that the elapsed time is this elapsed time is the total response time, and then is the total execution time of user applications. So actually our normal software or user software include many aspects of software operations, such as I/O operations, and then some operating system overhead, and then also CPU does not work every time. So that means that if the software waits for some response from the user, then CPU is in the idle state. So nothing is executed in the CPU processor. Also, I explained that the user software runs on the operating system, so it includes the overhead from operating system. On the other hand, the CPU time means the pure CPU execution time. So the CPU time is the response time of the thread or processor running on the CPU. It's a pure execution time. So then I said it's the execution time of a thread or processor. So actually the software or applications can be composed of several threads or several processes. But I said it's the execution time of processor or thread. So this is the pure CPU working time, pure CPU's execution time for the some thread. Okay. So let's talk about the CPU clocking. So actually the CPU or some computer processor is the digital device. So that means that this digital logic is working with clock. So if you took the digital logic design course, then I believe you already know about the clock. So most of the digital logic include the clock signal, and then this digital logic is composed of combinational logic and the sequential logic, such as D flip-flop, and then at the clock is input to this D flip-flop. So the electric signal is calculated or processed in the combination logic, and then the final result is sampled with the D flip-flop at the clock edge. So clock signal is very important on the digital logic, and then so in the digital logic, the combination logic execution should be complete within the clock period. So in this slide, this figure shows the example of clock signals, and then you can see the edge of the clock here. So this is the rising edge of the clock, and then this is the next rising edge of the clock. So I said that in the digital logic design, there is the combination logic, and then at the both sides of the combination logic, the D flip-flop is located. So, and then I said that at the rising edge of the clock, the result of combination logic is sampled. That means that this value of the combination logic is stored at the D flip-flop. So that means that the delay of combinational logic inside of these two D flip-flop cannot exceed the clock period. So this clock period determines the speed of this logic. So that means that the clock speed or clock frequency determines the speed of computer processor, because the computer processor is also digital, is composed of digital logic. So how can we measure the period or frequency of clock signals? So clock signal is the repeated signals. That means that this one or high and then low or zero of the clock signal is repeated again and again. And then we define that the time between this rising edge, start of the rising edge of the clock, and then the rising edge of the next clock is defined as the clock period, and then this clock period determines the maximum delay of the combinational logic between these two D flip-flops. So if we measure the time between the rising edge of this clock and then the rising edge of the next clock, and we can measure the clock period. So it's the duration of a clock cycle. Duration of the clock cycle. And then clock frequency is the inverse of clock period. And then this clock frequency is used for representing the speed of the CPU processor. So let's talk about the CPU time. This is the CPU running time. CPU time is simply CPU clock cycles, so that is the number of clocks spent running on the thread on the CPU, and then clock cycle time. Clock cycle time is the clock period. So if we measure the clock count while running some thread on the CPU, and then if we know the clock period, then we can simply calculate the CPU time like this. It's also obvious. It's also obvious. Okay. So this CPU time equation is so obvious. Clock, number of clock, and then clock period. And then most of the CPU speed is represented as the clock frequency, so we can use the clock frequency or clock rate like this, because the clock rate is the inverse of a clock period. So actually this CPU time is the CPU execution time, and then that means that this is the response time of thread running on a CPU. So with this CPU time, we can measure the performance of computer system. That means that if your CPU time is long, that means that this CPU was a computer system is slow. Otherwise, if the CPU time is short, it means the computer system has high performance. So how can we improve the performance of a computer system or CPUs? It's obvious, actually. We already know the equation of CPU time here. So if we reduce the number of CPU clocks, then we can improve the performance. It's like this, number of clock cycles. Or if we reduce the clock period, that means that if we increase the clock rate or clock frequency, then we can improve the performance. It's also obvious. So, hardware engineer or computer architect need to concentrate on improving the clock rate or reducing the number of clock cycles. But these clock cycles are determined by the software or algorithm or compiler in the instruction set architecture. So hardware designer need to consider this clock rate. But we cannot simply reduce this clock rate, because I said that the clock rate is determined by the maximum delay of the combination logic in the digital logic. So it's the maximum delay of the combinational logic. So it depends on some architecture of the computer hardware. Okay, so this is the example of CPU time. So there are two different computer systems, computer A and computer B. So, and then computer A has the 2 gigahertz of clock rate or clock frequency, and then CPU time is 10 seconds. So that means that if a given thread is executed on this computer A or executed on the CPU of this computer A, then it takes 10 seconds with the 2 gigahertz clock. And then the hardware designer wants to design a new computer system, computer B. And then the goal of this computer B is to reduce the CPU time to 6 seconds. So we can use the fast clock because we need to reduce this CPU time. But as the CPU time, as the CPU frequency is increased, the CPU cycle or CPU period no. Number of clocks can be increased. Is it because you need to learn about some pipelining, but if we design the deeper pipelining, that means that if we increase the stages of this pipelining architecture, then we can reduce the clock period. But the side effect of increasing the stage of pipelining is that the clock count executing the one instruction can be increased. So we will learn that effect later. In this condition, was some assumption is that engineers can use the best clock, but the clock cycle number of clocks will be increased to 1.2 of the original machine. So in this question, we need to calculate the clock frequency of computer B. So how fast must computer B clock be? So this is the equation of clock rate of computer machine B, or computer system B. Is the clock. So we can simply calculate the clock rate of computer B. It's the clock cycle of the computer B divided by CPU time of computer B. So this is the clock cycle of computer B. Okay, I will use the mouse. So it's the clock cycle of the computer B is the 1.2 of the clock cycle A multiplied by clock cycle B, and then this is the goal of CPU time. So 6 seconds. So with this simple equation, we can simply calculate the clock rate of computer system B. So firstly, we can calculate the clock cycle of computer A like this, and then then we can calculate the clock rate B. So this calculation is very simple because we can use only this equation. CPU time is the number of CPU cycles multiplied by CPU period. And then in this slide, I will talk about the CPI and instruction count. Then how does this clock cycle, So how can we decide these clock cycles? Clock cycles is the number of clocks for running some thread on a CPU. So this actually in the computer hardware, instructions are executed. So we can say that this clock cycle is very proportionally related to the instruction count of the thread. So, but if every instruction consumes one clock cycle, then instruction count can be equal to the clock cycles. But that's not always true. So we need some metric. So that is the cycles per instruction or clocks per instructions, CPI. So actually instruction count is IC, and then CPI is the clock count divided by IC, instruction count. So if you simply multiply these two metrics, then it's eliminated. This is the CC actually. So this is also obvious. So and then if we use this equation on calculating the CPU time, then CPU time is the clock count multiplied by clock cycle clock period. So CPU time is just the instruction count multiplied by CPI, is the cycles per instruction or clocks per instruction, and then multiplied by clock cycle time is the clock period. So it's just simply instruction count multiplied by CPI and divided by clock rate or clock frequency. So in this equation, the CPU time is this equation, and then in this equation, the CPI is important metric. So let's talk about let's talk about this instruction count and CPI. So instruction count of the program or thread is determined by the program. Program means the algorithm used in the program, and then instruction set architecture and compiler. So compiler means the compiler option or some compiler or different kinds of compilers. So this instruction count is the some number of instructions running under this thread. So, and then CPI is the average cycles per instruction or clocks per instruction. And then this CPI is determined by CPU hardware. So we will learn later in the chapter 3 or chapter 3, but you need to memorize that this CPI is determined by the CPU hardware. Why? So I will take an example from Intel i7 and then ARM processor. We know that ARM processor is very slow, and then Intel i7 is much faster than the Intel ARM processor. And I believe recently Intel renamed the ARM processor to Pentium, maybe. So let's think about this. Actually, the ARM process and then Intel i7 runs the same application, the same program. So because Intel only supports the x86 instruction set architecture. So if we compile these same programs with the x86 compiler, then it generates the same number of instructions. So that means that we configure with we use the same compiler configurations, and then ISA is actually the same because those CPUs use the same x86 instruction set architecture. So that means that the instruction numbers is the same. And then if we set the same clock frequency, however, the performance of this different type of CPU and the Intel i7 and the ARM is very different. So this difference comes from the CPU hardware architecture. So actually this i7 is designed for high performance computers, and then Intel ARM processor is designed for low power consumption. So performance is not an important factor of this Intel ARM processor. So that means that the different hardware is used, and then even if the instruction count is the same, and then even if the clock frequency is the same, the performance can be different. So this CPI is determined by the CPU hardware architecture. Okay, this is some example of CPI. So computer A, so we can in this slide, we will compare the performance of two different computer systems. Actually, the computer A, the cycle time, the clock period is 250 picosecond. It's about 4 gigahertz. Yeah, 4 gigahertz. And then CPI, clocks per instruction, is 2.0. So that means that on average, every one instruction consumes 2 clock count. Okay, and then let us computer B, the cycle time is the 500 picosecond is 2 gigahertz, and then CPI is 1.2. And then these two computers use the same instruction set architecture. So in this time, we will compare the performance of these two computers. So then we need to calculate the CPU time of CPUs or computers. So let's calculate the CPU time of computer A. Is the CPU time of A is the instruction count, and the CPI of A, and the cycle time A. And then we know that the instruction count is the same because it's the same ISA, and then same compiler option should be given. But we know that the instruction count is the same in this problem. CPI is different, is 2.0, and cycle time is different. So this is the I multiplied by 2 multiplied by 250. So I multiplied by 5 picosecond. Now, how about the CPU time B? Instruction count is the same. CPI and cycle time is the I multiplied by 6 picosecond. So we can compare the CPU time of A and B. And then we know that the A is faster because the CPU time of A is less than the CPU time of computer B. So we can just compare the CPU time performance of these two computers with the ratio of CPU time between A and B is the I multiply 6 picosecond, and I multiply 5 is about 1.2. So that means that computer A is 1.2 times faster than computer B. Okay, so I think so actually I plan to teach until some CPI example or performance summary, but due to some emergency situation, so I think the length of this video clip becomes so long, so I will stop here, and then I will leave the CPI the next time, and then I will cover this performance summary and then power burn in the next time, and then I will explain why the multi-core processor is used for the modern computer architecture or modern computer systems. Okay, sorry for inconvenience or some unexpected situation, and then I hope I want you to watch these videos, and if you have any questions, if you have any comment, then post your questions or comment on the Blackboard or Piazza. Then, so the problem is that we cannot meet on the offline classes for a while. So you need to utilize this online tools as if you need to utilize these online tools. So read the textbook and then watch the lecture video, and then if you have any question, and then post your question. Okay, thank you. 수고 많으셨습니다.